In this video, I am going to discuss about SCF theory, that is the self-consistent field theory, which is also known as the Hartree-Fock model. So this theory is basically used for the multi-electron atoms, okay, or the multi-electron systems. As we know that the Schrodinger's equation is valid for single electron atoms alone, okay. For multi-electron atoms, the Schrodinger's equation is not valid. And as we know that the Schrodinger's time-independent equation can be given by H psi is equal to E psi. So this is the Schrodinger's time independent equation, right? And particularly if we see the Hamiltonian H cap, then what we are going to see, H cap is nothing but it is the summation of kinetic energy and the potential energy. Kinetic energy and the potential energy, okay? So kinetic energy operator and potential energy operator, K cap plus V cap. So that gives you the complete Hamiltonian H cap. So K cap, which is kinetic energy operator, can be obtained from the kinetic energy formula, okay, half mv square. So we can write it half by multiplying with mass both on numerator and denominator. We get this value. So that is equal to mv means momentum, so we can write p square by twice m, and since it is operator, so we keep here operator symbol, okay. So as we know that p cap, the momentum operator, is equal to minus I h bar del y del x, okay. So this means that p cap square is equal to minus h cross square del square y del x square. So if we put this value here, then we can get minus h bar square by twice m del square by del l x square, okay. So this part is actually a Laplacian operator, okay, Laplacian operator. Now and the potential energy operator, its value is nothing but we can simply give it as potential energy, okay. The potential energy itself is the value for potential operator. So H cap becomes minus h bar square by twice m del square by del x square and plus the potential operator V cap. So now if we consider that we have a system, consider that H2 plus system, okay. H2 plus system is a system which is not which is 1 electron 2 nucleus, 1 electron 2 nucleus system. So consider, suppose this is one nucleus, say 1, okay, and this is nucleus number 2, and they are separated by a distance capital R. And consider we have, suppose here one electron is there, so there will be interaction between electron and the nuclei. So suppose the distance between the nucleus 1 and electron is R1 and nucleus 2 with R electron is R2. So what you can see here is that you can find the potential energy here. So potential energy here will be given by suppose interaction between first electron, I mean the electron and the first nucleus, that potential energy, if we consider V1, then we will get the value nearly minus z e square by 4 pi epsilon naught R1, and the potential energy as a result of nuclei 2 and with this electron gives, suppose B2 is equal to minus z e square by 4 pi epsilon naught R2, and there is also interaction between both the nucleus, that is the repulsive interaction. So that repulsive interaction, if you consider as a B dash, then we can get z e square by 4 pi epsilon naught R, okay. This distance of separation between the two nuclei is R. So that values we can put in this potential energy operator. So we can get H cap is equal to minus h cross square by twice m del square by del x square minus, you can put these values here, so it is minus z square by 4 pi epsilon naught r1 minus z e square by 4 pi epsilon naught r2, and then minus or plus z e square by 4 pi epsilon naught r. So this is the complete Hamiltonian for a electron of H2 plus atom. Okay, and so we can rearrange this Schrodinger's time independent equation as minus h bar twice m del square by del x square minus z e square by 4 pi epsilon naught r1 minus z e square by 4 pi epsilon naught r2 plus z e square by 4 pi epsilon naught r, and it is psi is equal to E psi. Okay, so this is the time independent Schrodinger's equation. Now let us consider the multi-electron system. Okay, suppose we have a multi-electron H2 molecule. Okay, the H2 molecule is having a multi-electron atom. So here we have two electrons. Consider E1 and E2. Nucleus we have 1 and 2. So distance of between this nucleus, if we consider r, and distance between this is r1 r2, and suppose these two electrons are separated by distance of r1 2, and there is also interaction between electron 2 and nucleus 1. So, and consider suppose the separation is we can consider it as r2 dash. Okay, and similarly between electron 1 and nuclei 2 we have interaction, so that is r1 dash. Let us consider. Okay, so same way we can apply the same thing we can apply to that values also. Okay, like in here you have to put the potential energies as a result of these electrons. So what we are going to get is that whenever we put that term here, okay, H K+V is equal to, we have already known that h bar square by twice m, and the divergence del square by x square. So potential energy we have, so you will get potential energy like z e square by 4 pi epsilon naught r1 minus z e square by 4 pi epsilon naught r2, okay, minus z e square by 4 pi epsilon naught r1 dash minus z e square 4 pi epsilon naught r2 dash, okay, plus z e square by 4 pi epsilon naught r plus z e square by 4 pi epsilon naught r1 2. Now the problem is with this particular thing only, okay, in multi-electron system with r12, because this r12 consists of coordinates of both electron 1 and 2 at a same time, or you can say simultaneously. Okay, they consist of the coordinate of both electron simultaneously, so which is against the Heisenberg uncertainty principle. Okay, so for this reason we cannot exactly define this term, this particular this is not an attractive repulsive term. Okay, this because there is a repulsion between E1 and E2. Okay, so this repulsion term cannot be explained due to the presence of coordinates of both electrons simultaneously. So now what happens, the Hartree-Fock or SCF model will tries to define this particular quantity. Okay, so what they have defined is according to them Hamiltonian is given by summation of H cap core I, okay, summation of this one, and here number of electrons, plus half summation of 1 by Rij, where I not equals to j. So according to the Hartree-Fock, or you can say self-consistent field method, they have assumed the Hamiltonian to be this value. Okay, so what is this one, H cap core I? Okay, what is this value? So H cap core is nothing but it is a single electron operator. Okay, single electron operator, and it gives us idea between the interaction between electron and the nuclei. Okay, interaction between electron and the nuclei. So H cap I core can be written as you can write minus half divergence square minus summation of Z alpha by Ri alpha. Okay, so here this is a kinetic energy part, kinetic energy of electron I. Okay, suppose the electron is I, then it is the kinetic energy of the electron I, and this part is the potential energy. What is this? Potential energy. Okay, potential energy between electron I and the nuclei, nucleus alpha. Okay, here Z is the charge of nucleus. What is this? Charge of nucleus alpha. Okay, and Ri is the distance of nucleus alpha from I is a electron. Okay, so this is the overall single electron operator. It does not give us value for electronic repulsion. Okay, it just gives us interaction of a single electron with the nucleus. Okay, this term gives us the interaction of electron with the nucleus alone. So that is the Hi cap core, and that value, this value is actually the potential energy that we have seen here, R12. Okay, now how we will define this? You see, since both the electrons are the coordinates of both the electrons are present at the same time, so what you can consider is that, suppose let us consider we have two electrons, right? Electron 1 and electron 2. So what we have considered that, let's suppose electron 1 occupies orbital psi j, okay, and electron 2 occupies orbital psi I, suppose. Okay, then the potential energy, suppose that electron 1 is somewhere in the field of electron 2 which occupies psi I. Okay, so the potential energy that is experienced by this electron 1 as a result of this electron 2 can be defined in this way. Okay, that potential energy can be written as written in form of Coulomb operator. What is this? Coulomb operator. So Coulomb operator is one term which is denoted by J cap. Okay, and it is nothing but it is a potential energy experienced by one electron, say suppose electron 1 due to electron 2. Okay, so we have introduced here potential as I mean the Coulomb operator. So what we will see here is that Coulomb operator J cap, suppose here we have considered J cap J, okay, J cap J, and psi sorry, it will be I. Okay, I have considered here it will be I and psi j 1. It means that the potential energy that is experienced by the electron 1 which is in the orbital psi j. Okay, So that will be given by your integration of, we can write psi I 2 or psi I square, psi I whole square by, psi I square, which is occupied by electron 2, and the distance r1 to d tau 2. Okay, that is the potential energy that is experienced by the electron 1. So more broadly we can write J cap I psi j 1, that is that means this Coulomb operator of electron 2, that is why we have written here I, okay, which is experienced by electron 1 occupying the orbital psi j. That particular quantity will be given by integration of this particular value, okay, psi 2 1 by r1 to d tau 2, and then we can also multiply as psi j 1. So that is the potential energy that is experienced by the electron 1. Similarly, we can consider for electron 2. If we want to consider, then we can consider that the electron 2 will be experiencing the, will be experiencing the force as a result of electron 1. So here we write J, which is occupied by electron 1, and it is acting on electron 2I, right? So in that case it will become integration of the square of this quantity, okay, psi j 1, as a result of, that means this potential energy, it signifies the potential energy as a result of the electron 1 which is in the orbitals psi j d tau 1, and this whole quantity you multiply with psi I 2. Okay, so that will give you the, this value is nothing but this is the potential energy, that is the potential energy that is experienced by electron this 2, which is in the psi 1 orbital. Similarly, we have one term that is called exchange operator, okay, which is given by k cap. So exchange operator is, suppose we have considered here the exchange operator for I, okay. So psi j1, so that quantity exchange operator is simply given by this particular term, okay, integration psi I2 psi j2, okay, and 1 by r1 to d tau, okay, and here psi j2, okay. So basically that is the exchange operator. Exchange operator, if you want to understand, then suppose we have two electrons we have considered, okay, suppose p1 2, okay, then on acting this operator, if it acts on 1, then exchange operator, what it becomes, p1 to 1, okay. This is nothing but exchange of orbital, okay. So as you see here, that here the orbital psi j1, okay, now here it becomes, sorry, this will become psi I1, okay. That means there are two orbitals, right, psi I and psi j. We have considered psi I is occupied by electron 2, psi j is occupied by electron 1. So exchange operator means psi 1 is occupying in psi j also, and it occupies here also in psi I also, okay. So that is why here psi j1, it becomes here psi I1, and similarly this electron 2 can also exchange their this one orbital, okay, psi I psi j electron 2, and this is the radius between them, distance of separation between the two electrons. So after combining this Coulomb operator and exchange operator, you can see that the Schrodinger, the Hartree-Fock equation, this particular term, after combining, what we will get, that H cap will become nothing but it is becoming summation of n H cap core I minus summation of, here we have number of MOs, okay, molecular orbital, and 2 J cap, okay, minus K cap. So that is the overall value that we can get for the Hamiltonian, okay, overall value that we can get from the Hamiltonian. If we solve this second part, then we will get this value, okay, we will get this value. And here we have to give 2 because there are 2 electrons in each orbital, right? So now finally, suppose we are to consider this value can be written as H cap summation of n I core minus summation, this will become 2 J cap J, I here, okay, minus K cap I, and this whole term psi J1 is equal to E psi J1, okay. So that is the overall, you can consider overall equation, modified equation for multi-electron system, okay, for electron 1 which is in the psi J orbital, okay, that will be the eigenvalue equation for that electron. So this particular term is given by F cap, okay, and this F cap is known as Fock operator. So what we can modify it again, it becomes F cap J psi J1 is equal to summation, it is energy 1. So this is the Hartree-Fock equation. This is the Hartree-Fock equation, okay. Now there is one more modification to this equation, that is known as Rutan method. So what is Rutan method? According to the Rutan, the molecular orbital psi can be regarded as the summation of, with coefficient, okay, psi I, suppose summation of all the atomic orbitals, okay, summation of all the atomic orbitals. So this is the atomic orbital which is here known as basis function, okay, basis function. So you know the LCMO, linear combination of atomic orbitals, LCAO, am I right? So in that, what we have assumed is that all the atomic orbitals, they will combine to give us molecular orbital. So this molecular orbital, this is here molecular orbital, is regarded as the combination of all the atomic orbital basis function, which is given in this way, okay. And here we have n, and this n is nothing but this is the number of orbitals, okay, number of atomic orbitals, okay. So this is the basic assumption here, and because of this assumption, if we put the value of this one here in that equation, then what you will get, f cap j, this, suppose this is a psi j, okay, we have considered it psi j for psi j, then it becomes summation of ci j and pi I j, okay, that is equal to e summation of Cij pi ij, okay. Now what happens, we will multiply in this equation with here it will be j only. We will multiply this above equation with pi star I, okay, on both the side. On both the side we will multiply it with this equation, I mean this orbital. Then what we will get, pi I star f cap j summation of n Cij pi j is equal to e pi I star n Cij and then pi j. So this term can be modified again, or we can, yes, we can modify it again, and we can write like Cij in the form of bracket, okay. Then we will get pi I f cap j pi j, and here we will get E, which is the energy. Then here we can write pi I pi j, this value we get. And now we have to remember one thing, that this particular term is known as resonance integral, okay. Resonance integral, that is given by Sij, okay. So we can write here Sij. So ultimately Cij, and this may be replaced by f cap I j, okay, f cap I j, and that is equal to E and Sij, okay, Sij. This is the particular equation. Now we can make it again in this way, okay. Cij f cap ij minus E Sij, that is equal to 0. So this is giving us a linear homogeneous equations, okay. Now using the variation principle, and also using energy minimization, if you do not know what is these terms, I can explain you in another video, okay. Using these two terms, using these two quantities, we will use these quantities to here, or approximations here. Then what we are going to get, we are going to get determinant, okay. We will get determinantal equation, and that determinant equation becomes secular determinant equation, okay. Secular determinant equation, that will become like this, okay. F ij minus E Si j, determinant of this particular term for n number of f I j n, okay, minus E I Si j n up to n. Similarly here also, again it will extend up to f I j n minus E Si j n it will just extend. And here we will get Cij dash, okay, that quantity we will get, which is equal to 0. And for non-trivial equation, this must be set to 0. So what we will get is, we will get like this, and this can be further modified in this way. Okay, you can just see here f11 minus es11. S11 means what? S11 means psi1 psi1. Okay, and what is this? It means SII. It means SII. Okay, so psi I, this is nothing but this is. Okay, sorry friends, I have to apologize for the inconvenience, because I have already wrote this one, okay, but I did not know. I was going on explaining this part, but I did not know that my video became off at that time. So again I will explain this part. So here we will put 1 and 2, okay, like similarly for here f12 we get minus s. I was explaining this one, no? SII means it is a 1, okay. SII, that is, you can write psi I by psi I in the bracket form. So since psi is a normalized wave function, so that value gives 1 ultimately, okay. So here we can omit that S11, okay, this is 1, and the rest are like simply the same, okay. F1n minus ES1n, that is equal to 0. Similarly for this one, it it becomes 2 1 ES 21, and here again becomes F22 minus E, and again here S22 means again this will be of this condition again, okay, then it becomes 1, so we can omit this one also. F2n minus ESN 2n, right? So this will just go on up to Fn1 minus ESN1, then here it becomes Fn2 minus ESN2, and so on, okay, up to Fnn minus ESNN, that is equal to 0. So this is ultimately the equation, that is the secular determinant equation that can be obtained. And our the Rutan method, this is a Rutan extension, okay. The Rutan equation can be regarded as this, I mean this particular equation can be regarded as the Rutan equation, okay. This one Cij F_Ij is equal to Esij, okay. This equation is known as Rutan equation. This is just an extension of the Hartree-Fock equation. This is the Hartree-Fock equation, okay. By considering that all these orbitals, that means by considering that psi is a, we know it is a molecular orbital, okay. So that molecular orbital is formed as a result of linear combination of atomic orbitals. So that is what we have considered here, okay. That is what Rutan has considered by considering the basis function psi ij. So that gives our Rutan approximation, okay, and this equation here is the Rutan equation, okay. Thank you.